Thank you, Tobias, for the introduction. Thank you, everyone, for coming here for this talk early in the morning. So today I have the pleasure to talk to you about how we can make private multi-label classification. And for standard data sets such as MNIST, we just have to give a single label per a given image. So here, in this image, we just have a single digit being 7. However, for many real-world data sets, such as medical data sets, we have to usually assign more than a single label per image. So in this case, a given patient might suffer from more than a single pathology. So now let us imagine that there is a patient who comes to a doctor, and doctor has not had such a case before, and is not confident about his or her prediction for this patient. So the doctor wishes to consult with many other doctors or hospitals and takes X-ray of this patient and sends this X-ray to many of these collaborating parties. So these collaborating parties, being other doctors or hospitals, they use their ML models to give labels to this given image. So then we aggregate in our framework these labels from many collaborating parties and return the final aggregated answer to the querying party, in this case being the doctor. So in our framework, we formalize this workflow to be able to provide this private consultation. However, in this framework, there are two issues. The first one is that first of all, we don't want this patient to reveal his or her data to all the collaborating parties in the plain form. And also, this patient will have to sign many documents to be able to provide this data to these collaborating parties. It's a lot of paperwork. Second thing is also that collaborating parties, these hospitals, they don't want the liability for managing the private data of this new patient. So what we have to actually do is that we have to provide for this new patient's data confidentiality. Second problem is that these collaborating parties, they train their ML models on their own patients' private data. So what we don't want is to reveal this private data about other patients to the querying party, being this doctor. So we have to provide privacy for this data that were used to train the ML models. So how do we tackle the first problem? So for the first problem, we use the framework which is called CAPC, which stands for Confidential and Private Collaborative Learning. And here we apply private inference to be able to do this inference on encrypted data for this new patient. So this is done. And then the second problem still remains how to provide privacy for the data on which we train these ML models. So now let's start from the beginning. What's happening is that each of these answering parties, they return a binary vector, which is basically their votes for this given image. So here, for example, we have positive votes, which are ones, and negative votes being 0. So there are two methods how we can provide this private multiple classification for this scenario. So the first method is called binary method, in which we consider each label separately. And second method is called power set, in which we take into account the whole binary vector as a single class. And I will delve deeper into these two methods. So first, let's consider a single label, in this case, the first label. And we have these votes from each of these answering parties. So the first party gives us vote 1, positive vote. We take the vote and create a histogram where we have on the y-axis vote counts, on the x-axis possible values for a given label. So here we have these three parties. Two of them vote positively for this label, and one of them votes negatively. And now the question is how we can provide privacy when we want to reveal such an answer. So what we do is actually we also apply the Patay framework that Francisca described perfectly in the previous presentation. And we add Gaussian noise according to privacy guarantees that we have to ensure. So in this case, we add this Gaussian noise on top of these vote counts, and then we take also noisy argmax to reveal the final answer. So we do the same histogram for each of these three labels. And ultimately, what we achieve is that we cast this multiple classification into multi-winner election. And each voter has a single vote per a given label. OK, so we also considered alternative methods to binary one, which is in this case power set method. So in power set method, we consider all the possible, in this case, three value binary vectors. And because we have three labels, then we have 8 such possible classes. And note that in this case, number of possible classes grows exponentially to the power of n, where n is the number of possible labels. So once again, we create histogram for these 8, in this case, possible classes. And in this case, two of these answering parties, the first and the third one, they voted for the fifth class. We have 2 votes for this class, and only one party voted for the second class. Again, on top of these vote counts, we add Gaussian noise to ensure that we privately release this answer to the given classification. So let us now consider a different example of voting. And we do that to compare directly these binary and power set methods. So in this case, we have different ballots or votings from each of these answering parties. And when we consider these votings per label, then actually each of these answering parties, they would return as a majority the positive vote. So it occurs that the binary method returns true plurality, which means that we choose the most voted for value for a given label. And note that actually this selected output is just a binary vector of all ones, and this binary vector is not present in any of the answering parties. However, this is the correct answer in this case. So what is happening is that every single teacher doesn't have to be expert in all of these possible pathologies, these labels, but collectively they have this knowledge to answer this classification correctly. However, power set method is only approximate to plurality. So in this case, we observe once again that we have different votings from each of the answering party. And then we don't return true plurality in this case. Finally selected labels in this case are 101, which are actually present in one of the answering parties. And here, because each party votes for a different class, the final answer actually depends on how much noise we add on top of all of these vote counts for each class. So in this case, we select class 5, but there's only one vote for this class. Okay. Another aspect is that we have also different types of data. So it can be the case that data are uncorrelated, so every single label is independent. And what we show in our work is that in this scenario, the binary method is optimal, and we formally show this optimality. However, if we have noisy or strongly correlated labels, then the power set method performs better. So imagine that you have, for example, these 2 last labels that are strongly correlated. So it happens that if we have one label, other ones also present in our outputs. So then we can just, instead of having separate classification per label, we can just treat them together. So this saves us, for example, on the privacy cost. And when we now delve into the real data sets, such as Pascal-Vogue, what we observe is that, in general, there are not many positive labels for a given data point. So, for example, in Pascal-Vogue, on average, there are only 2 positive labels out of 20. So how can we cater to these real-world requirements? So what we actually do, we apply clipping to the number of positive votes. So how does it work? So first, let's consider binary method. So we have, just for ease of exposition, we just have 3 labels. And we have this single vote from a given answering party being all ones, right? So this is this B sub J vector. And what we actually want to do is that, because we should have up to 2 positive votes for this classification, so then we want to clip these votes in the same way as you, for example, do in the PhD. So we want to ensure that the squared norm of this vector is 2, and then we clip this vector B sub j with all ones to this shown vector B sub j at the bottom. So this is how we do clipping for binary method, and we also show that this clipping actually is optimal in the L2 norm. Then, how do we apply this vote clipping for power set method? So in this case, if we have these all possible 3 labels being positive for each answering party, then we have 8 possible classes. However, if we limit that each answering party can vote up to 1 positive label, then the number of classes for this method increases to only 4. So here we have much fewer classes for power set if we apply this clipping. And now to compare these different methods for the real data sets, we use different metrics, standard accuracy metric, but for this task of material classification, there are even better ways how to assess the quality of these methods. So one of them, for example, is balance accuracy, which is a mean value between true positive rate and true negative rate. We also use area under the curve, which is ratio between true positive rate and false positive rate, and also we use mean average precision to compare these different methods. So first of all, we here show that for the Pascal data sets, which has 20 labels, we achieve the best performance with the binary method. And this is across all of these metrics. Additionally, also our power set method performs relatively well, even better than the standard PhD approach. And we also incorporated our private multiple classification into the CAPC framework. And then what we here observe is that before our method is this first row in this table, is that before we use CAPC, we have this performance for a single collaborating party. And then after this party collaborates with other let's say, doctors or hospitals, and we achieve higher performance across all of these metrics once we do this collaboration. Also, we tested this method for medical data sets such as chest X-ray or mimic data set, and again we observe the same outcome, that if we enable collaboration, then after that we can have higher performance for our model. So to sum up, we show that we can provide for this data of a new patient confidentiality through the CAPC framework. And second aspect is that we also designed new methods, binary and power set, to enable private release of this multiple classification. So with that, thank you for your attention. I'm happy to answer any questions.
So let's thank our speaker.
So we are also joining, so if you want to also work on such topics, please join our lab. We also created Francisca a new lab at CISPA, so you are more than welcome to apply.
Which questions are there in the room? No questions. There's one question.
When you're capping the number of total classes that a teacher can vote on, what is the teacher supposed to do in the plurality method if they actually have more
yes.
positive labels?
Yes, very good question. So yeah, this is this part. So once you have this classification on a single answering party level, right, they have actually some threshold per each single label. So then they are required to release up to that many votes. So then they just have to just have higher threshold to release, for example, up to that many votes. Great question.
Further questions online or in the room? So let me ask a question. So watching these two talks side by side, it actually does create the impression that this is all part of a bigger research project and research endeavor. Is that impression correct, or am I mistaken there?
Yes, we have common agenda, and indeed this is part of
what's your agenda?
Yeah, so in this case, of course, we are focused on how to really make this privacy really applicable. For example, in this case, we are focused on medical domain. We talk about this different individuals. They might have different privacy requirements. And also we want to cater to this real-world requirements, such as here, medical data with, for example, chest X-rays.
So maybe one more question from the room. Otherwise, I'm going to ask questions. I'm a nasty person, so please save him. Okay, so
okay, thank you very much.
How aware are you of this being used in practice? For example, being adopted in hospitals. So is there a need for machine learning in hospitals? We had in the other talk the example of data sharing in a hospital.
How do I see that to be applicable? Sorry.
Like, is machine learning in hospitals already practically used? So are you enabling for a problem they have, or are you creating technology to enable?
Yeah, so actually we have a specific use case in Toronto. So actually around back to the many hospitals, and indeed we are collaborating with them, talking to them about like what are the requirements, what they really need, and based on these problems, actually we try to solve them using these techniques.
Thank you. So let's thank our speaker again.